Welcome to the video on intercepts, and we're going to be focusing specifically on X and Y intercepts during this video. Also, as a general overview, we've dealt with a lot of different types of graphs already. So if I had a line, usually a line has one intercept. It could have two intercepts. If it hits like this, it has an X-intercept and a Y-intercept. You could have a parabola. And remember, a parabola could have two intercepts, two X-intercepts and a Y-intercept. A parabola could have one X-intercept but no Y-intercepts. You could have one Y-intercept but no X-intercepts. There's a lot of different possibilities. You could even go beyond that and have a cubic function that has one X and one Y-intercept. You could have an absolute value function, could have two X-intercepts and a Y, and it ends up relating very much and acting like the parabola. You could also have a polynomial function that is something higher than the power of 3. And this is where we're going to be going, especially second semester pre-calculus. You deal with functions that could look like this. That could have 1, 2, 3, 4 X-intercepts and one Y-intercept. Or you could have something that looks like this, that has multiple intercepts as well. So for this time being, we're probably going to be dealing with linear, quadratic, cubic, but this right here in green is going to be intercept second semester, which definitely will make a comeback. So in terms of definition, intercepts are solution points, and again, solutions, as we talked about, make the equation true. And these specific points are at which the X or Y value is 0. For instance, the X-intercept is technically as defined as a solution point in the form a, 0 or x, 0, and it touches the x-axis. So the reason that y is always 0 is, if you think about it, if you graph a bunch of x-intercepts and you name some points, we have 1, 0, 2, 0, 3, 0, -1, 0, and notice that the y value, no matter what, is always 0. And so if you would like to find an x-intercept quickly, all you need to do is plug in y equals 0 and you can find them. If you would like to find the y-intercept, that means that you're dealing with any point along the y-axis. And again, it is a solution point in the form 0b or 0, y. Now it says set x equal 0, and that is because if you name some points up and down the y-axis, 0, 3, 0, 2, 0, 1, 0, -1, and so on. Again, please notice that the x value is always 0. So if you'd like to find any y-intercept quickly, you just need to take x equals 0. Now, I do want to point out that this is an opposite relationship. When you're finding the x-intercept, you want the x to actually be there. So you need to plug in 0 in for y. However, when you want to find the y-intercept, you want the y to actually exist, so you plug in x equals 0. So what you plug in for 0 is the opposite of what type of intercept you're really finding. So let's do some thinking questions here. What are other words or phrases that are the same as x-intercepts? And some of these I've actually already mentioned in past videos. I would like you to pause and see if you can write down any synonym for an x-intercept. Please pause now. Here are 3 examples that I came up with. The most common one, I would say, is solutions, because we've been talking about it off and on during this unit. Roots is also very, very popular, as well as zeros. All of these I will be using interchangeably throughout the rest of the semester and second semester, and you should always know that they mean the same thing, where it crosses the x-axis. What is the least amount of x-intercepts a graph can have? And draw an example. And what are the largest amount of x-intercepts a graph could have? So again, I would like you to pause the video, and I would like you to draw a quick sketch of what you think, or what is a graph that represents the least amount of x-intercepts you can have, and a graph that could represent the most amount of x-intercepts you can have. And I will come back with my answers in a little bit. So please pause now. All right, so here are my answers. What is the least amount of x-intercepts a graph can have? Well, I said 0. And here are 2 examples to prove that. If you have a horizontal line that is parallel to the x-axis, you have points all along that line, none of which touch the x-axis. So that means I have no x-intercepts if I have a line. And also, if I have a parabola, the vertex is here, facing away from the x-axis. It's not touching the x-axis, so there's 0 roots, solutions, or x-intercepts. On the other hand, what is the largest amount of x-intercepts you can have? I actually said infinite, and here's 2 examples to prove that. If I happen to have a horizontal line directly on top of the x-axis, that means that all of its points are the same as the x-axis, so there are infinite answers because this line goes forever in each direction. Also, a graph you have not come into contact with yet, but you will this semester, this is the graph of a sine or a cosine function. You would be familiar from geometry that those are trig functions. A lot of this semester we're going to be dealing with trigonometry, so I thought I'd throw this in here. A sine function or a cosine function is going to keep oscillating around the x-axis, so it's going to hit the x-axis infinite times. With that in mind, I'd like you to pause the video and answer these questions as well. What is the least amount of y-intercepts a graph can have? What is the largest amount of y-intercepts a graph can have? And please try to draw an example of this. So please pause your video now. All right, so for these answers, I actually got the same final answers. The least amount of y-intercepts you can have is 0. If you happen to have a vertical line that is parallel to the y-axis, it never hits it, so there would be 0 y-intercepts. If you had a parabola on its side, it also never touches the y-axis, so that's 0 as well. An example for the largest amount of y-intercepts, I again said infinite. If you happen to have a vertical line directly on the y-axis, it would hit infinite times or infinite solutions, so that's how many is possible. Now, something I do want to point out to you about all 3 of these examples is all 3 are not functions. You might recall the vertical line test from past math classes that said if you have one x value that goes with more than one y value, it is not a function. So these are graphs, yes, but they're not anything that we would normally graph. I would say this is the most normal of the 3, but all of these are not functions. This does not pass the vertical line test, definitely has more than one y value that goes with an x value. This does not pass the vertical line, one x goes with 2 y's, and this also does not pass the vertical line test. So 0 and infinite are still correct answers, but these are technically not functions. Just a little side point. Example, find the x and y intercepts of this function. Now, if I would like to find the x-intercept and I would like to find the y-intercept, from the first couple pages of this video, remember that if I want to find the x-intercept, that means that y is 0, and if I want to find the y-intercept, that means that x is 0, based on the position on the graph. So what I would like you to do is pause and algebraically find what the x-intercepts are and find what the y-intercepts are. You may need to factor. Please pause now. All right, so here are my answers. Notice that I wrote all my answers as points because intercepts are always solutions, which are always points. The x-intercept, if I set this quadratic equal to 0, I ended up factoring 2 numbers that multiply to be -3 and add to be -2 are -3 and 1. Set both these parentheses equal to 0. My 2 x-intercepts were 3, 0 and -1, 0. The easier one is to find the y-intercept. If you plug in x equals 0 into the function, 0 squared is 0, 2 times 0 is 0, so you're just left with -3. So the y-intercept is at -3. Now, even though this was not asked of you, I want to point out that with these points, you could graph a quick sketch of this parabola. To use the previous video in mind, because this is squared, I know it's a parabola, and I know because it's positive in front, it's facing upwards. So if I came down here and made a sketch, I know that my parabola is facing upwards. I know that the 2 x-intercepts are at 3, 0 and -1, 0, and the y-intercept is at 0, -3. This won't be perfect because I don't think it turns here, but my graph would probably look something like this, at least a brief sketch. Definitely not a perfect picture, but the whole point is just prediction anyway. The last example, how can our calculator help? Well, if I was given this example and I still want to find the X and Y intercepts, what I want to point out to you is that it is generally always easier to find the Y-intercept first, because if I plug in X equals 0, I would get this. And I'm honestly even wasting time writing it out, because if I plug 0 in to anything cubed, I know this is going to be 0. 0 times 8 is 0. So this whole thing is going to become 0. This is going to become 0. This is going to become 0. So I'm generally left with the last number. So I'd get 0 plus 0 plus 0 minus 9. So that means that my y-intercept is 0, negative 9. And you could even do that without much work. You could do that completely in your head. The x-intercepts, however, are generally harder to find. A lot of the time you have to factor. So if I said 0, because I'm trying to plug in y equals 0, equals 8x cubed plus 26x squared plus 3x minus 9. You might remember the skill of factoring by grouping, because there's 4 terms, all of which cannot be added together. If I tried to factor by grouping, I could take out a 2x squared, and I would be left with 4x plus 13. And here I could take out a 3, and I'd be left with x minus 3. Now, unfortunately, these parentheses need to match in order to factor by grouping, so that did not really help me find my x-intercepts because I can't keep factoring. So that's when the calculator can help. So if you don't have your graphing calculator with you, if you could please pause the video here and grab it. Okay, now that you have your calculator, what I would like you to do is please graph the function 8x cubed plus 26x squared plus 3x minus 9. I already did so. Let me pull this calculator down so you can see it. I have an online version, pretty cool, right? Remember that if you would like to put a cubic in, you would just press caret to the third, and the x squared button is right here. I also want to point out that if you want to put any x's in, here's the button here to get any x value. Okay. So after you graphed it, your graph should look something like this. And the highest power of this polynomial is to the third. Notice that there are 1, 2, 3 places that it crosses the x-axis. That is generally always a connection we want to make. Now also in terms of predictions, we want to figure out what these roots are exactly. But it looks like this root is exactly on 3. This root is between negative 1 and 0, and this root is between 0 and 1. So I'm going to write that down. My 3 roots, it looks like one of them was exactly at negative 3, one of them was between negative 1 and 0, and one of them looked like it was between 0 and 1. Let me just take a look again just to make sure. Yes. So we can find these roots exactly, and to do that we would like to go to this calculate menu. So we would press second, trace, we would get to this menu, and the synonym for a root or a solution is a 0. So we would have to press 2, and the graph is going to ask us specific things. Let's focus on the root that's between negative 1 and 0. It's asking to the left, so the biggest number or the closest number to this root to the left is negative 1. So we would press negative 1 and then press enter. Now the calculator is asking, if we're focusing on this root, what is the closest integer to the right? Well, we said 0. So we would go to 0, press enter, and then the calculator wants to guess. So you press enter for a third time, and it tells you that the 0 or the root is at negative 0.75 comma 0. So I'm going to write that here. The root ended up being exactly negative 0.75 comma 0. So one of the roots is this, one of the roots is negative 3 comma 0, and we can find the third root doing the same thing. So this last root is between 0 and 1. So if I go to second, trace, 0, the left of that root is 0, enter. The uppermost bound of that root is 1, press enter. Press enter again, and the root is exactly at 0.5, 0.